Swayam Prabha, free DTH channel for education.
Hi students, welcome back to the online video lectures of the medical imaging course. This is a second video lecture on CT image reconstruction. In the last video what we discussed is, let's say you have a 2D object and you are taking a parallel projection of that object on a one-dimensional space. Then what we have explored in the last class is how is the one-dimensional projection. Suppose given that your parallel projection is done at an angle theta with respect to the x-axis, what is the relationship between the 1D projection of the object, 2D object that you have got with respect to the original 2D object? That's what we have discussed in the previous video lecture. What we will do in this lecture is, let's take a relationship between the same two entities now in the frequency domain. In other words, again consider a 2D object. You have a two-dimensional continuous time Fourier transform of that object, and then you have taken a one-dimensional projection through a parallel set of rays that are coming at an angle theta with respect to the x-axis, and now you compute the one-dimensional continuous time Fourier transform of this projection, and how is the Fourier transform of this projection is related to the two-dimensional Fourier transform of the given two-dimensional object. That's what we are going to discuss here. Although we are discussing it here in the context of CT, this theorem plays a vital role even in case of MR imaging, but used in a slightly different way. We will come back to that while we are discussing with MR. And this theorem is known as Fourier slice theorem. This is also referred to as central cross-section theorem, and sometimes this is also referred to as projection slice theorem. Okay, with that background, let's go to a notebook mode and let's see more details about this Fourier slice theorem. Let me restate the problem again that I am just now mentioning. Let's say we have an object in 2D. Let this be your object in 2D. Let's call it as f of x comma y. So this is your x-axis and this is your y-axis. Now let's say I compute the two-dimensional CTFT of it. So we will move on to kx ky space here. This is your kx ky. Let me call this as capital F of kx comma ky. Assume that now I am taking a parallel projection of this object at an angle theta here of this two-dimensional object. Let me call this as g theta of x prime. This is your x prime axis, and this is making an angle of theta here. If you want to plot the same thing here, so this is your x prime is in this direction here, okay, and this angle is theta. Now to this g theta of x prime, so what you have here is g theta of x prime. To this g theta of x prime, you compute the one-dimensional CTFT of it, and we'll have something here with varying values of kx, and this let's call it as capital G theta of kx. And the question is, how is this related to f of kx comma ky? That's what we are going to explore in this video lecture. As we did in the previous video lecture for CT image reconstruction, here also let's start with a simple case where I am taking a projection of this f of xy with theta equal to 0. So for this object, I am taking a simple projection here like this being my x-axis and this being my y-axis. Assume that here I got, let me simply call it as g of x, this is x-axis, and let the two-dimensional CTFT of it, let me again call that as capital F of kx comma ky, and let's now compute the capital G of kx and try to establish what's the relationship here. So as you notice here, we are considering a special case here with theta equal to 0, where your detector is at an angle theta equal to 0. So what did we say for f of xy? The two-dimensional CTFT of it is f of kx comma ky, and for g of x, the one-dimensional CTFT of it is g of kx. Let's write first the expression for capital F of kx comma ky given its value in the two-dimensional spatial domain. So you have, let's say, x varying from minus infinity to plus infinity, y varying from minus infinity to plus infinity, f of x comma y into e power minus j 2 pi times kx into x plus ky into y dy dx. Now we need to find out the Fourier transform for g of x. So first let us write g of x expression given f of x comma y. How do you get that? You take integrate for a given value of x, you integrate it over all values of y. So for a given value of x here, you could write y varying from minus infinity to plus infinity. You integrate further f of xy with respect to dy. Now write the given g of x. Now write the continuous time 1D continuous time Fourier transform g of kx, which would be equal to x varying from minus infinity to plus infinity g of x into e power minus j 2 pi times kx into x dx. You already know the expression for g of x, so substitute g of x value here, right? That would give you the one-dimensional Fourier transform of g of x is equal to x varying from minus infinity to plus infinity, y varying from minus infinity to plus infinity, because that's what g of x is, into f of x comma y. Let me just put it a little later, this dy. Before that, let me write e power minus j 2 pi kx into x, and now let me write that dy followed by dx. All right, so now take a look at this expression f of kx comma ky and this. How are they related? Well, all that is missing is this term ky into y here, right? Other than that, so in order, if I have to get g of kx from f of kx ky, what should I do now? Y I cannot put it's not a constant, something varying from minus infinity to plus infinity. So if I put here this ky value to be equal to 0, then these two expressions are going to be same. So in other words, let me write it this as x varying from minus infinity to plus infinity, y varying from minus infinity to plus infinity, f of xy into e power minus 2 pi of kx into x plus 0 into y times dy dx, right? So you compare these two expressions, that implies your g of kx is equal to f of kx comma ky equal to 0. In your Fourier transform expression of f of x comma y, you just make ky equal to 0. That would give you the expression that would be same as g of kx. This is very interesting result. Why is it so? So what's happening here? Take a closer look here. So if you are taking projection in a way that you are filling this value here, this value for kx equal to whatever value is there. Okay, don't confuse that there is a value here. We are not plotting here. Okay, but this exactly would give you this values. So if your theta equal to 0, then this value here, this line across along this, you will get all the values there. They will nicely, these all values. Okay, so I have not plotted here because I can't plot 3D, but something like this. This is exactly these values, whichever you get it, kx equal to 0. Now this is a special case we considered. Next question I am going to pose you is, suppose I am not going to do a projection at theta equal to 0, but parallel projection at some other angle, which means, say I am projecting it like this now, and let's say it is at an angle theta, right? And assume that this is giving me, now I call it as g theta of x prime. This is your x prime, I call it. This is x, this is y, and of course now this is your x prime here. In other words, if you rotate it, then it is exactly same as the earlier one. So now you have, like earlier, 2D CTFT of this f of xy, which we refer to as capital F of kx comma ky, and similarly the one-dimensional CTFT of g theta of x, which let's call it as capital G subscript theta of kx, and how are they related? This is not that difficult as it appears, provided you make use of the earlier knowledge that we gained while we are dealing with the continuous time Fourier transform. Suppose you are taking at an anti-clockwise direction of theta a parallel projection. Is that not equivalent to taking a projection at theta equal to 0, but where you have instead rotated your object in the clockwise direction by theta? Yes, of course, both would be the same one. Next question I am going to put is, for f of xy, assume that here I have a two-dimensional CTFT of capital F of kx comma ky. If I rotate it, let's say by theta, this f of xy, that is, let me call that new f1 of xy, which is obtained by rotating f of xy by theta, then let's call that new Fourier transform of that new function f1 of kx comma ky. How is this related to this? This is something we worked out, or at least we discussed in our earlier classes. You can figure out to other sources as well for the derivation of this. This is pretty straightforward. What would you get if you do this? This is also a rotated version of f of xy. Also the Fouriers, if you rotate the object by an angle theta, the Fourier spectrum of that also gets rotated by an angle theta. That's the result. Okay, so if you make use of that result, what can you say now for the sake of better illustration? Let me draw here f of xy rather, and then let's plot where this g theta of xy would correspond there. Assume that I have some f of kx comma ky. What is now going to happen here is, if you have taken a projection at theta angle, then here also if you take at an angle theta, that is where this g theta of kx would correspond to. Very interesting result. Okay, this again, based on this inference, this logic, you could extend this here as if you are rotating this object and taking a projection parallel to the y-axis, then it would be this. Since that now you rotate by theta, that would give you this projection which is at an angle theta. So this in fact would correspond to this, which kx here at certain angle. This is a very important theorem. Now even by taking Fourier projections of a given object, you could start filling the kx space, kx ky space here of the original 2D object. Just from the 1D Fourier transforms of the projections, you could fill the space of the two-dimensional Fourier transform. If you are taking a projection at theta, it goes at theta. Suppose if you have taken a projection at 90 degrees, this would give you all the value at kx equal to 0 along this, so on and so forth. That's how you could fill. The implications of it would become even more clear by the end of this lecture. So before that, let me just write what this is referred to as again. This is called as Fourier slice theorem or projection slice theorem, or another word for this is central projection theorem. It is referred by all these names. So as I mentioned, what it says, let g theta of x prime be the projection of f of xy at some angle theta, then f of kx ky be the two-dimensional Fourier transform of f of xy. Then what you could say is, one-dimensional Fourier transform of this function is in fact two-dimensional Fourier transform of kx ky along the radial line which is there at the same angle. This is the very important theorem here. Okay, so let us again come back to our notebook. Let's make few more observations here. Let's say your 2D object f of xy, you are taking a projection like this, which is giving you, let's say, z0 of x. We figured out that this would corresponds to all the values along this kx line of f of kx comma ky. But however, this being your sensor or detector of the x-rays, which requires a certain, but it could have sensors would take a particular region here. So in that way, this values which you have is in fact a discretized version is what you would be having the moment you have z0 x here. So that correspondingly, that would eventually result in having the samples here at, let's say, some regular intervals here. Now let's assume that you are making another projection, okay, like this, all the values here, and constructing the g theta of x here or x prime here, this we call it as x prime. Now what would happen? This would give us now the values along the same theta. So this is your theta here, okay, or this is your x prime here. So that's theta. Now this is where it would give. Again, this would give you values because of the sensor discretization. You have values at regular intervals here. Now another thing you would do now is you keep varying theta. So with that, you get these value at different values here at different discretizations here. Of course, one you could for instance have here as well. So this is how you could acquire the values along this axis. If I want to obtain from here f of xy, what should I do then? So right now if you look at it, my samples that have been acquired in the space of f of kx comma ky are like this. So this I could draw, for example, a line here, and then here, here, here. I could draw more if you want in between, and here across each points these are like this. Some acquisitions have been done like this here for the reasons of the discretizations that come as a result of your sensors occupying certain length limitations of that sensors, size of the sensors. You would be getting a samples of this like this. Now if you want to compute f of x comma y, you need to acquire these samples at uniform grid. So let's say here, here. So if I interpolate, let's say, the values that I am getting as a result of various projections there onto a uniform grid of points which I am showing here, in that case, to those uniform grid points, the inverse DFT of it, then you would, what it would give you is, essentially, provided you have enough samples, what you get is f of xy. So that's something you could do in case of CT. You simply take projections at different angles, you get something like this polar coordinates, you take enough angles there, let's say few more samples here, then you interpolate them onto a uniform grid based on its neighborhood values of this kx ky space. And to that uniform grid of points you compute the inverse DFT of it, and that would give you, of course, to be more precise, it would give you f of m comma n there. Anyway, the moment you are storing it as an image, that's f of m comma n. That's what you would be getting, right? If it is an MR image, you will come back to it a little later. You would be acquiring your signal in kx ky space, so you have a control over your kx ky space acquisition. Okay. On the other hand, in our current CT imaging, what you would do is you take projections of it. So you could do, if for example, one thing that you could do is interpolate your kx ky space. Interpolate your kx ky space. It's almost equivalent to converting from polar to rectangular coordinates. Do you see any problem here? See here at low frequency regions, okay, around the center, you have enough number of samples around the center, but as you move away from the center, you could notice you have less number of samples from which you need to interpolate. So there is a problem. Interpolation becomes erroneous as you move on at high frequencies. So the problem here is interpolation at high frequencies is a problem. So I hope that's clear to you. The main message there is, if you are having a projection, your sensor is at an angle of theta. Fourier transform of that projection, one-dimensional projection, corresponds to the kx ky space acquisition at that particular, at the same angle theta, and that's how you could fill your kx ky space. This works okay, but as you move on away in the kx ky space, as you are going to the high frequencies, then there is an issue of interpolation becomes erroneous. And to deal with this, again, people won't be exactly doing in this manner by going into the Fourier domain in case of CT images. So there are other methods, and hopefully we will discuss one more method in the next video lecture. We'll stop here. Thanks for watching. See you in the next video lecture. Bye. Take care.